the main idea of this chapter is we're going to learn about the behavior of electrons, and then meaning energy, the way electromagnetic radiation interferes and behaves with electrons, particle wave duality of light, kind of physicsy. We're going to get pretty physicsy. And then we're going to take all that information we learn about the different states of energetic states of electrons, and how they emit light when they're brought down to energy levels, lower energy levels, etc. And we're going to take that and put it into the periodic table, meaning take all those concepts and relate it to electron configuration. And we're going to be able to determine the electron configuration of most elements pretty precisely, and know their quantum numbers and things like that. So let's start off simple with light, electromagnetic radiation. So there's a huge electromagnetic radiation spectrum, or just called EM spectrum. And this whole EM spectrum consists of things that we know and we see it every day. Visible light consists of X-rays, gamma rays, UV rays, microwaves, cell phone radiation, radio waves, infrared, stuff like that. And a lot of stuff we can't see. Most of the EM spectrum we can't see. And every one of those forms of light is photons, and they have waves and particle properties. So meaning that, like a flashlight, the particles that are coming out of a flashlight of photons, they're actually particles. They're massless particles that have energy. And the energy is in this thing called a quanta, which we'll learn about the equations for that in a few slides. And they actually behave like a wave, just like sound. Oh, I'm going to zoom in on the slide. So here's what I could do. Do that. So they behave like waves and particles at the same time. Now, all of them through a vacuum have the same speed. That's the speed of light, which is a good constant to know, but they'll probably give it to you on the test. 3 × 10⁸ meters per second. So that's the speed of light in a vacuum. Now, light in different types of electromagnetic radiation could go slower. It can't go faster, but it could go slower based on what medium you're putting it through. For example, if you were to put light through a prism, you would get the different spectra. That's because they would separate by frequency, and you'd get different colors of light. So every color of light has a distinct wavelength and frequency associated with it, and they have a relationship as well. And here's what they are. So here are different properties of electromagnetic radiation. They all occur in waves, and they are particles as well, but they have these main 3 components to the wave, which is an amplitude, a frequency, and a wavelength. So the amplitude is just the intensity of the light. It's not characteristic to the light. Basically, it's how bright the flashlight is. That's the amplitude. The wavelength is the measure of the distance covered by the wave. So in the next slide, I'll show you an example of a wave. And the distance from peak to peak, or trough to trough, is the wavelength. And that's usually measured in meters. But for visible light, and really for the entire EM spectrum, we're going to be talking nanometers. So visible light spectrum goes from about high 300s, let's say 380 nanometers, all the way up to 800 nanometers. So we would have 800 times 10 to the negative 9 meters, or 8 times 10 to the negative 7 meters. So anyway, then you have frequency. So frequency is how many times the wave occurs per second. So you could have two concepts with this, with different types of radiation. You could have ones that are big and slow, meaning long wavelength, low frequency, or you could have the opposite, meaning long or low wavelength and high frequency. Those are the most dangerous, and dangerous meaning to us, and carcinogenic and things like that, because frequency is directly proportional to energy. And we'll see that when we talk about the equations for the energy of the photon. But frequency is dangerous. Wavelength, we have big wavelengths, that's no problem. So in essence, they're inversely proportional. All right, so here is an idea of a wave. Now, here's what I'm going to do. Screen sharing stopped. Oh, I don't have one of these days where it does this. All right, so here you have a wave, and you can see the wavelength is the distance between, or people are joining. Come on, it's important to come on time. Okay, so we have the distance from peak to peak, that's the wavelength. The amplitude is the height of the wave. And then the frequency is how many waves occur per second. And what that means, how am I going to visualize that, is I'm going to write another wave down here. This wave is going to be like that.
I'm sorry, Professor. I just wanted to let you know I'm here.
Okay, that's fine. All right. So imagine, so it's a difficult concept to distinguish between frequency and speed. They're not the same thing at all. So imagine all light moves the same speed, and it does in a vacuum, 3.0 times 10 to the 8 meters per second. So imagine these are all on the same piece of paper, both of these two waves. And you're taking the paper and you're moving it across the table. And you're reading the paper at a certain point. So from this wave, or maybe can you guys, oh, my video's off, whoops. Yeah, now you should see me on my laptop. Go there. Yeah, right. Oh, it'll come up eventually. But basically, I'll wait for that to come up. All right, now you can see me. All right, so if you can imagine you're following along the waves and you take a point on the wave and you're just moving a piece of paper underneath that point. The point on the wave would go like this, up and down, and oscillate. So the speed of that oscillation from top to bottom, that's the frequency. For example, the top wave will have a very low frequency because if you move it across a piece of paper, the wave would go by slowly. And on the same piece of paper, you have the lower wave, which has a higher frequency because you move it across the same exact speed, and a lot more waves go by. It goes up, down, up, down, up, down, up, down. So that's what we mean by frequency. It's the amount of cycles of the wave per second if you're moving them along at the same speed. So, and you can see how that directly correlates to wavelength. Obviously, the one that's going to have the shorter wavelength is going to be faster because when you move it across the page, the waves go by faster. So they're inversely proportional to one another. That's the best way to put it. And here's the equation for it. So here's one way to write the equation. You have the frequency. So let's do a little Greek letters here. So this is lowercase nu. This V, it's like a cool looking italic V. That's lowercase nu, and that means frequency. Frequency, it's measured in hertz or cycles per second. That's the same thing. Then you have C, which is the constant speed of light. So 3 times 10 to the 8 meters per second. And then you have lambda, which is a Greek letter, and that means the wavelength. So I'll put WL, and that's usually in meters. Then if you divide meters per second by meters, you just get per second. That's where you get the frequency from. So that's one way to write the equation. You can also write it as C equals a product of the frequency times the wavelength. That's how it's traditionally written, but either one is cool. Josh, you can also do wavelength. Yeah, I guess so. But yeah, if you think about it differently, that's cool too. Anyway, so that's that. And here's some examples of some waves. We kind of went over this already, but if you have increased frequency, you're going to have a decrease in wavelength. So you see how the bottom one in blue has a short frequency, or sorry, a large frequency, short wavelength. And then as you go to the red, it has a longer wavelength, lower frequency. And then bright and dim, this just changes the amplitude of the light. Doesn't really change anything about the wavelength or the frequency. So now color. Color is important too. So there's a color spectrum, and it's part of the visible light spectrum for EM radiation. So we can just cut to the chase, and we can take a look at the spectrum. So here it is. Now, our eyes can only see a very small percentage of it, just the visible light. Meanwhile, animals, some animals, such as bees, for example, like bumblebees, they can see UV light. So they can see in this region over here. Over here. But most animals and vertebrates can see, if they could see at all, they see in the visible light spectrum. But I mean, most animals have a lot better eyesight than we do. Like my cat, if it's completely pitch black in the room, she knows exactly where everything is. It's not by smell, because if I throw something at her, she like dodges it. Like I don't throw things on my cat. Like I play fetch and stuff. Like she knows where it is. So they have great eyesight. They take in a lot more photons than we do. That's why they have good eyesight. Kind of like exposure on a camera. Like most animals have like a longer exposure, and their exposure takes in more photons. So their images are brighter. Anyway, so the most important thing to know about these radiations is that there's an inverse relationship between wavelength and frequency. So for visible light, you have red light, which has the lowest frequency, highest wavelength. So it's big and slow. Then you're going to have violet, which is small and fast in the visible light. When you get beyond that, you get to danger level, right? What comes after violet? Ultraviolet, which is from the sun. UVA, UVB light, UVC is synthetic, but it also causes cancer and can kill different microbes and stuff. They're actually doing that on planes right now for COVID. Is they're using the UVC wands to kind of kill all the microbes that are on the plane. So planes are actually very safe, and there's no threat of getting COVID from a plane anymore. So it's pretty cool. Hopefully the plane stocks will go up. I have some money in there. But anyway, so UV rays, and then when you get further, X-rays and gamma rays, you get more dangerous because the frequency increases. So gamma rays cause cancer, X-rays can cause cancer as well. So I'm assuming, is it possible to increase the speed of frequency for a long wave? No, you'd have to decrease the wavelength. And so to break that law, you can go faster than the speed of light, but you can't. So, why can't you? It's physics. Just talk to the physics professor about that. Anyway, so gamma rays are dangerous. That's like nuclear reactors, Chernobyl, stuff like that. You get cancer, and those rays have such a high frequency and such a high energy, they can go right through your body, and they damage DNA on the way through. So sometimes you accumulate enough of that damage, and you get permanent mutations in your cells, which could then lead to cancer if they're not checked. And that's my field. But let's talk about chemistry. All right, so then you go the other way, or the Hulk, exactly. Then you go the other way to less dangerous. You have infrared, which is, if you're a Call of Duty fan, like the heat-seeking, the thermal scopes, that's infrared. And then you have microwaves, radio waves, and things like that. Cell phones are kind of in between radio waves and microwaves. So common misconception about microwaves and cell phones is that they can cause cancer. If you stand in, I'm sure many of your parents told you if you stand in front of the microwave, you can get cancer or get sick. That's not true, because microwaves, they are contained within the microwave, but even if they weren't, it's still not enough frequency to even penetrate your clothing. So don't worry about that. And same with cell phones too. So cell phones, that's a big thing that's been going around the last couple of years, is that people are worried that they're, let's say, sleeping with their cell phones next to their head could lead to brain cancer, because there was a study that was put out that said there's a 2% correlation of brain cancer, but that's not significant at all. And it's not true. It's just, you do the study again, you can get -2. But yeah, Josh made a good point, and my other class made this point too. 5G. So we don't know what 5G is doing. That's the new cell phone waves. I think it's higher frequency, because it's better. It transmits more energy and transmits faster. So we're the guinea pigs for that. I have 4G still, so I'll stick with it for a while. It's fast enough for me. Anyway, so then your radio waves, they've been around for hundreds of years. We've been okay. Not hundreds, but maybe 100, 150 years, and we've been okay. Okay, moving on. So you can take these waves and you can have different interference patterns with them, meaning you can concatenate them on each other and they can cancel out, or they could build up on each other, meaning you can add them up. And if you add them up and you get a bigger signal, you get constructive interference, which means another word for that is being in phase. And I'll show you what that means in the next couple of slides. Then you can have destructive interference, which means if you add two waves that are the opposite of each other, let's say you add this wave to this wave, you would get a flat line. It's not a good flat line, but you get the point. So it's a flat line. And this is called out of phase or destructive interference. Or you can get a combination of the both. If you shift this over a teeny bit, you'll get like little wave over here, then it'll be stronger over here, then it'll be little over here. And you get kind of a destructive interference, but it won't be as much. Then you shift it over more and more, the destructive interference decreases and it becomes constructive. So you can imagine if you have two waves, you're keeping one stationary, moving the other one, it'll be a combination of constructive and destructive interference as you're moving the wave. And then it can go up and go down. Literally everything in this chapter, if it oscillates, everything oscillates. Every signal is up and down. You add two signals, they become up and down, and then you move them across, it becomes more up and down or less up and down. It's all oscillatory. So here's an example of that. So you have waves that are in phase, you get constructive interference. If you add them up, it just gets more. And then if you have waves that are out of phase, you have destructive interference, which is less. All right, next, diffraction. So when you have waves that encounter obstacles or other particles, such as if you're like Pink Floyd, Dark Side of the Moon, you go through a prism, then this is called diffraction. And there might be an opening in that barrier. In the prism's case, it goes through the barrier, but it perturbs the wavelength a little bit. Then you get diffraction. And there's different diffraction patterns. This isn't too important, so I'm going to go briefly over it. But basically, this diffraction proves that light has a wave-like nature. Photons, or even if you have sound, for example, both of those have a wave-like nature. Sound is just a wave, meanwhile light is a wave and a particle. But it'll do this. You shoot a light beam or a sound wave at a wall that has a little slit in the middle, the wave will restart at the slit or diffract. That's what that means. So you could also have two-slit interference, which means if you do this, have a light source and it goes through two different slits on the same barrier, you get a pattern of constructive and destructive interferences, like I was saying before. And actually on the wall, even though both lights are showing, you would have a oscillation of light to dark, light to dark, light to dark, because this represents the waves that are hitting each other from either slit becoming constructive or destructive. And that just keeps, depending on the positioning of this film, it depends. So yeah, that's interesting to just know that exists. All right, now this is important not just to know it exists, but to know formulas and and what it means. So it's called the photoelectric effect. Now, this is the reason why if you put tinfoil in a microwave, it starts to spark. So what the photoelectric effect is that metals are observed to emit electrons when certain energy of electromagnetic radiation is shined or is incidented, if incident light touches their surface. This is called the photoelectric effect. So what will happen, and don't write things, let's just take a look at it. So look at figure A. Light comes in and it has to have enough energy. Oh, professor, what's enough energy? Well, it depends what the metal is. Some metals keep their electrons more than others. They hold on to it more. This is called their binding energy. So every metal has a minimum binding energy. The energy required to knock off one of its electrons with light, or with anything. It's just an energy. The light can supply that energy from the equations we'll see in the next couple of slides. When the light supplies enough energy to go over that binding energy threshold, you get an emitted electron. The electron gets kicked off the metal. So it's kind of like you're scraping it off. You have a scraper and you're trying to scrape a sticker off the table. If you do it with a half-assed job and you're kind of weak about it, it's not going to come off the table. If you have weak photons or photons that are of lower frequency radiation, they're not going to do the job. But if you take one really good hack at it and put a lot of energy into it, you'll take that sticker off the table. Same thing. You're taking electrons off a metal if you put in enough energy from that photon. We have a question. Does it correlate to molar mass or anything? Not really. It's just specific metal properties. It's kind of random, honestly. But there is a general trend. It's not really a trend, but the trend, if I had to pick a trend, the trend would be group 1A has the lowest binding energy because it doesn't really want to hold on to its electron. It gets rid of it very easily. Group 2A tends to be a little bit more binding energy. And then as you go to the right, some of the transition metals, that's where it really gets funky. But I know 1A has the lowest binding energy compared to 2A. Okay, cool. So now equations and stuff, or what does this mean? Here's the written what I just said. So for a given metal, no electrons are emitted below a certain frequency of light. That's actually not correct. It's below a certain energy, not necessarily frequent. So that's true if you're talking about one photon. So I'll explain this. Normally, when we talk about the photoelectric effect, we're talking about the energy of one photon knocking off one electron from the metal, right? So in that case, yeah, the energy of that photon has to be strong enough to knock off the electron. But what if you have a lot of weaker photons that gain and that input more and more energy until that threshold energy is reached to knock off one electron? That's also possible. And this is why microwaves, if you put tinfoil in the microwave, it sparks. Because the microwaves themselves, one microwave is not nearly enough energy to knock off one electron from tin, if it was tinfoil, or aluminum. It's not tin, it's aluminum. But if you have, and that's why when you put the microwave on, it takes like a couple, like maybe a second or so. It's not instant that it starts to spark. It takes like a couple seconds. That's why, because the microwaves for that couple seconds builds up the energy enough for electrons to come shooting out. And if you don't do this at home, but if you were to try and put a small piece of tinfoil and then time it, it would be almost instant. It'd be maybe like a second. A bigger piece of tinfoil, it would maybe take 4 to 5 seconds. And that's because the microwaves are going to be dispersed through the billions and billions of electrons. That energy is going to be kind of absorbed by the metal up into a certain point. For a smaller metal, for a smaller physical piece of metal, that point will happen a lot sooner than a larger piece. So the photoelectric effect is not just one photon to one electron, even though conventionally that's what they mean. But it could also mean just pure energy getting put into that electron, or into that metal, to get rid of that electron or to flick it off. So just keep that in mind. Now for the canonical example, which means the normal example, you have one photon kicking off one electron. And this energy threshold we call the minimum frequency, or we call it the binding energy, minimum binding frequency, whatever, there's different names for it. Also, so that's one part of it. Now, we all understand the electron comes off, but when an electron comes off, electrons, unlike photons, have mass. If they have mass, that means their speed is not, first of all, it's not the speed of light, and their speed is quantifiable. And you could actually calculate the speed of the electron that comes off. So I'm going to write an equation that's very general, but if you have the energy of the photon, so put EP, energy of the photon is going into the metal. Let's say it's above the binding frequency. The energy of that photon will be the binding frequency because it needs that level of energy to knock off the electron. But it has more. So that more energy gets translated into kinetic energy of that electron. So that's where we get this equation for. This phi means binding energy. We'll see that. Plus kinetic energy. So basically what's happening is you have the photon going with a specific wavelength, specific frequency, specific energy that can be calculated. If that energy is enough to knock off the electron of the metal, it will first reach the binding energy. That's binding energy. Then every piece or all the additional energy will be converted to kinetic energy of the electron to give it momentum, or sorry, to give it kinetic, same thing, give it kinetic energy to leave. That's what the photoelectric effect is. And you're going to have to do calculations with that. And we'll do an example in a couple slides. It was what? Oh, EP, energy photon. Right. So here's where you're going to learn the equations for the energy of the photon. So this is Einstein's explanation of it. Now, Einstein said that basically light can have energy packets called quanta. And they basically call it a photon also, so a quanta. Now, the energy of the photon is directly proportional to its frequency, like I said, and that proportionality is based on Planck's constant, which is a very important constant in physics. And Planck's constant is weird. It's very, very small. It's 6.626 times 10 to the negative 34 joule seconds. That will be given to you like every other constant, but it's an important one. And if you do examples in practice, you'll memorize it. But that's Planck's constant. So if you take Planck's constant, h, it's called h, times the frequency, I'll put freak, times the frequency, that equals the energy of that photon. So with this equation, you can directly find from either the wavelength or the frequency, you can find the energy of that photon. If you have the wavelength, okay, you can easily convert that to frequency and then convert that to energy of the photon. And that equation's here. That's another way to write it. You can replace this V, which is frequency, by C over lambda. And you get either one. Another way to write this equation, so let's say this. I have a photon with a certain frequency, and I don't just have one photon. I have an entire mole of photons. What would I do to this equation to figure out the energy of a mole of photons? Or two photons. It doesn't have to be a mole. Anybody? You have an answer. Multiply. Boom. Got it. Good job, Josh. So you're basically going to multiply it by whatever constant that is, whatever amount of photons you're trying to find out the energy for. So this equation in some textbooks is rewritten as E equals NH nu, meaning N is an integer number of photons. If you're trying to find out the energy of one photon, it's 1. A mole of photons, it's Avogadro's number. And then H is Planck's constant, and then this nu is the frequency in hertz. So you can figure out the energy of a photon using that equation. Okay, so here's what I just said. The ejected electrons are going to have kinetic energy in the photoelectric effect, because whatever photon had enough energy to kick off the electron, the rest of that energy is getting converted to kinetic energy. So that's where you get E photon equals phi plus kinetic energy of the electron. So I'll put kinetic energy E, just so you don't get confused. And then you can find the kinetic energy for that. So it's very important to understand conceptually how that works, instead of just memorizing equations, because the way they're going to put it on the test, on I guess the final exam, would be they're just going to write it in a paragraph form. You have this thing that has an energy, has a frequency of this. You have metal that has a binding energy of this. How fast was the electron when it got kicked off? So you have to think, all right, photoelectric effect. That means I'm taking the electron, I'm taking the photon, got a certain energy, hitting the metal. The metal has a binding energy, so it's got to go above that binding energy. Whatever is remaining is the kinetic energy given to the electron. If nothing is remaining or it's negative, that means the photon didn't have enough energy to knock off the electron at all and was below the binding energy, which is totally possible. They might ask that as well. So let's do an equation practice. This is from the homework. So the photoelectric effect for a certain alloy has a threshold frequency of 8.4 times 10 to the 14 hertz. For light of this frequency, find the energy of 1 mole of photons. So this isn't exactly photoelectric effect yet. This is just a practice of how to find out the energy. So what I would do is I would use my energy of the photon equation. EP equals NH nu. So I have, this is just 1 mole of photons, all right, so N is equal to 6.022 times 10 23rd. Planck's constant, who can tell me Planck's constant? Good, 6.6, oh, I wrote it wrong. 6.626 times 10 to the negative 34 joule seconds. And then our frequency is going to be right here, 8.4 times 10 to the 14 hertz, which is just per second. So I'll actually write it that way. I'll write 1 over seconds. So if you multiply this out, look what happens. Seconds will cancel, and this is just 1 per second, and then you end up with the answer in joules. So whatever this number is, oh wait, I know what it is. Oh, look at sneaky me. Whoa, look at that. It's 335. So yeah, you get 335 joules. Now, another important thing, when you're using your calculator and you're multiplying or dividing scientific notation numbers, be careful. Put parentheses around everything. So take Avogadro's as a number, take this one as a number, and then take this one as a number. Put everything in parentheses to be safe. In multiplying, it's fine. You can multiply everything across. But if you're dividing, that's when it gets tricky. Because if you're dividing, you have to put it in parentheses, or else it will multiply the entire quotient by 10 to the negative 34. And your exponents will get all messed up. So make sure to keep an eye on that. Any questions on that? Or any questions on concepts we went over so far? We're going to do a question on, I think. Are we going to do a question on? Oh, we aren't. Okay. Well, let's do one anyway. All right, so now we're going to do a question on photoelectric effect. So using this question, using this information. Now, let's say our metal, so we're going to give one more piece of information. Our metal has a binding energy, I'll put metal phi equals 250 joules. What is the kinetic energy of electron? So you take this mole of photons, or what's the kinetic energy of the electrons? You take this mole of photons and you shoot them on a metal. A mole of electrons come off. The binding energy for a mole of electrons to come off is 250. What is the kinetic energy of those photons, or I'm sorry, of those electrons? And we have, yep, Adi, good job. So you take 335 minus 250. So you take the total energy of the photons that are shining on the metal. Subtract the energy that's needed to kick off the electrons in the first place, which is 250. The remaining is going to be the kinetic energy of the electrons. Not the kinetic energy of each, but yeah, 335 minus 250, what does that equal? 115? No, 95, 85, yes, 85. All right, so that 85 joules. Another follow-up question would be, what is the average kinetic energy of an electron? This 85 joules represents 1 mole of electrons. So what you'd have to do, what would you have to do? The 85 represents kinetic energy of 1 mole of electrons. How would you find per electron? Yeah, divide by Avogadro. Exactly. Good. Good job. All right, so you divide by Avogadro's, you get a really small number, and you get the answer right. Okay. Any questions on that? No? Okay. All right, so now we're going to talk about the Bohr model of atoms. So now we're going to take all this information on radiation and energy and electrons and how electrons behave with light and energy, put that into atoms, atomic talk. So you've seen these before. These are neon, like you've seen the neon beer signs before, right? So the way that works is there's a current and there's energy that goes through these gases. And it's really the neon beer signs are combinations of argon, neon, and other different gases, xenon, other different noble gases that make color. Depending on their combination percentages, they make different colors. Most of them are actually argon. Argon's blue. So what we were saying here is that once you put energy through it, it emits light. Why the hell does it do that? Well, we're going to learn about that. And here's exactly why. So let's say you put energy through a hydrogen lamp. So a sample of hydrogen gas, you're putting a current through it. that current is enough energy to make the hydrogen shine a certain color. Once you separate those wavelengths with a prism, you get 3 bands. And this is called the hydrogen emission spectrum. Now, that doesn't answer the question that I said. The question I asked was, why does this happen? I just showed an example of it happening again. All right, so the next slide, I believe, is why it happens. Nope, that's not true. But anyway, there's one for barium. Here we go. Here's why it happens. No, so Adi, no. Mass spectrometer uses magnets. Yeah, it's not a. So a mass spectrometer is not actually a spectrometry technique because it doesn't use light really. I mean, you can hook it up to different types of analyses to use light, but it uses mainly magnets and ionization techniques to separate isotopes based on, or any atom really, any molecule based on charges and fragmentations. But anyway, so the Bohr model, he's saying that this guy Bohr is like, all right, the electrons, we'll go back. Can you go back? This one. Yeah, they make light. Okay, cool. Yeah, just know that. All right, so what's happening, we have a better chart. Here we go. This is why. So this is why not only hydrogen or barium, but every single element has an emission spectrum. Because if you put energy into these electrons or into these atoms, what will it do? It will excite their electrons. The amount at which the electrons are excited determines the color and how many bands of light are emitted. All right, that's kind of right, but let's go a little bit deeper. So what happens really is that according to Bohr, we can simplify the atom and the electron placement of the atom into different energy levels, where you're going to be sick of me saying the term energy levels by the end of next week, after chapter 9, and even after today. So we have energy levels. We have a lot of them. We have 1 through 5 here, but there's actually like a billion. Electrons reside at each of the energy levels. For hydrogen, there's only 1 electron. It resides at energy level 1. Now, depending on the amount of energy given to hydrogen, that electron could jump. It can actually jump from energy level 1 to 2, from 1 to 3, from 1 to 4, 1 to 5. So if that's the case, what happens next? So all I did was I took energy, stuffed it into the electron. That made the electron get really excited because, oh, I have a lot of energy now. And then it went up to either 2, 3, 4, or 5. For hydrogen's case, it only goes to 3, 4, 5. Yeah. Oh, yeah. Oh, like an outside current. It's coming from an external source. So if I were to take lightning, for example, that's what lightning does. If I were to take lightning and put it through a gas sample, it would be bright. That's why lightning is bright, because you're putting a lot of energy through a gas sample, and it is exciting all the electrons in that sample. And then when they come back down to ground state, they emit light. So you're taking external energy. Okay, good question. All right, so that was a really good question, because that cat's out of the bag. So how does the electrons emit light is when they come back down to ground state after they're excited. Because they come down, they're excited for nanoseconds. They come down almost immediately. When they come down, where is that energy going? It has to be emitted. And it's emitted in the form of visible light. Sometimes UV, but mostly visible light. So that is how these bands form. And there's a correlation between the amount of electrons, or how large the atom is, to how many bands it shows on its spectrum. And we can see that when we compare hydrogen and barium versus helium. Same thing, same concept. Helium only has 1, 2, 3, 4, 5, 6. Barium has a ton because barium's bigger. Barium has more electrons on different energy levels that all get excited at once to other different energy levels, and then they all come down and make a bunch of different lines. So in general terms, the bigger the element is, the more lines it's going to have on its spectrum because it has more electrons. So when they get excited and then when they come back down, they're going to emit all different types of light. So that's cool. Does that make sense? Yeah. All right. So now this is a really good slide to study from for that concept. So what we can do, we can actually calculate the amount of energy lost when the electron gets excited and it comes back down. So we know light or energy goes in, electron gets excited, then it comes back down almost immediately, energy is released. How much energy is released? We can figure that out with this equation. So this is the Bohr model equation, and it tells us based on this constant of negative 2.178 times 10 to the negative 18 joules, and based on the atomic number of the atom in question and the energy level that the electron's on, we can tell exactly how much energy that electron has just by knowing the energy level and what element it is. So by extension, we can say that, all right, if hydrogen, we take hydrogen atom, we take an electron on energy level 3, and it goes down to energy level 1, what's the difference in energy? All right, we'll take energy level 3 energy in this equation, then energy level 1 energy in this equation, subtract the 2, we get the difference in energy levels from 3 to 1. So using it, this is an important equation, it will be given as well, but know what it means. So Z is the atomic number. For hydrogen, it's 1, helium is 2, etc. Then the proton number. And it's Z squared over N squared. And N is the number of the energy level, 1, 2, 3, 4, etc. And so we're going to do an example of this together, and then I'll give you a minute to do one on your own. Okay, so let's say wait, are we doing one? Did I lie? Oh, no, I didn't lie. This one's different, though. Oh, we might do that. Okay, question. So no, N is just the one energy level. So you could, here's what you can do. You could set up two of the equations and do kind of like a N final minus N initial kind of thing. Like this equation, right? So what you can say, I mean, I've said this before when it comes to equations, I think very simply. So I would just take the information for energy level 3, put it into one equation, take the energy for energy level 2, put it into another equation, subtract the 2, just so I don't get complicated. But if you want to solve this problem, which is the energy change for an electron going from energy level 3 to energy level 2 in hydrogen, how do you calculate it? All right. So delta E equals E final minus E initial. E final represents when N equals 2. E initial, actually, oh wait, wait, what did I just say? Yeah, I said it right. E initial is when N equals 3, because it goes from 3 to 2. And this number is going to be negative because the system is losing energy, right? It's losing energy to visible light. So you're going to put those numbers in, and since it's hydrogen, you're going to have the Z equals 1. And then you put those numbers in, and you solve it, you get negative 3.049 times 10 to the negative 19 joules. So that is the amount of energy emitted when an electron of hydrogen goes from goes from N equals 3 to N equals 2. N is energy levels. So just to clarify that. Furthermore, and this is what I would expect on homework assignments and everything, they can ask, what color is that light? They could just blatantly ask you, what color is it? How would you figure that out? Anybody know? You have the energy of it. How'd you figure out what color it is? Yeah. By how far it's going. Yeah, so but based on the energy number itself, you can figure out the color. So let's see what, you're on the right path. The table, no, not. Look at the spectrum chart, kind of. Okay, you're kind of touching. All right, so what is characteristic of each color? What are the two things that each color has that's different from the other colors? Like the traits. We learned about two of them. Wavelength and frequency, right. So which one of those, wavelength or frequency, has anything to do with energy? Frequency, good. So from the energy that's released, we can reverse engineer that into our energy of a photon equation, which they do here. And we can say that the wavelength of it, or we could find the frequency of it, and we could also find the wavelength of it. From the wavelength of it, or the frequency, but most likely the wavelength, we can determine the color. So if we were to reverse engineer the equation, solve for lambda, which is the wavelength, you get lambda equals 6.57 times 10 to the negative 7 meters, or 657 nanometers. And 657 nanometers is a pretty long wavelength, right? Because I said that the visible light spectrum of wavelength goes from around 300, 380, 400, all the way up to 800. So 657, it's kind of in the orangey red area. So, and from looking at the chart, you'd be able to see that. You don't need to memorize that. So that's how you do that. Any questions? No? Okay. All right, so this question, I'll let you guys do this on your own. Let me read it first. So the charge of an electron is that negative 1.602 times 10 to the negative 19 coulombs. That is a constant from physics. For the photoelectric effect, how many microamperes, so how many microamps? So that's, remember, what's micro? 10 to the negative 6, right? So microamps. How many microamps, and each amp, they tell you each amp equals 1 coulomb per second, of electrical current are produced when the metal is bombarded with that many photons, a lot, each second. Assume that each photon is sufficient energy to eject 1 electron. You're being told that you have 6 times 10 to the 13 photons each second. That's important. 6 times 10 to the 13, put photons per second. Now, it tells you that assume each photon has sufficient energy to eject 1 electron. This means that you're going to have this many photons hitting per second. This is a very instantaneous process. So you're going to have 6 times 10 to the 13 electrons being emitted per second. If that's the, not per 6, per second. If that's the case, and we know that the charge of each electron based on the first sentence is negative 1.602 times 10 to the negative 19, we can multiply this and we can figure out the charge per second in coulombs. Negative 1.602 times 10 to the negative 19 coulombs. Now, coulombs per electron. So we can see electrons will cancel out. So what's the answer for this one? 6 divided by 1.602. We have a winner. 2 winners. Good. Negative 9.612 times 10 to the negative 6. Negative 9.6. I'll just put negative 9.6 times 10 to the negative 6. This is coulombs. Coulombs per second. All right. Now, we know we're converting to how many microamperes. So before we get to microamperes, let's just convert to amps. We know that 1 amp is 1 coulomb per second. So if we have negative, or we can make it positive because these are amps are going to be positive. See, as note, all currents are reported as positive values. So currents are positive. So 9.6 times 10 to the negative 6 coulombs per second times, we know that 1 amp is 1 coulomb per second. So we just convert. Honestly, it's an easy conversion. So if this many coulombs per second is equal to amps, so we have 9.6 times 10 to the negative 6 amps. So how many microamps is that? Remember micro, what prefix or what does that mean? Good, 9.6. Good. So yeah, exactly. Multiply times 10 to the 6th, and you get 9.6. And oh, let's see what the answer is. It's probably gonna be a little bit different because I rounded. 9.612. But yeah, same thing. Okay, cool. So I see that only like 3 people are participating. That's not good. Try to participate. It'll only help you. Honestly, if you don't and you're not engaged, I mean, you could totally watch the videos later. It's fine. But if you have questions, I'm not going to be there in the videos. It's not a live video. Now is a live video. So you can do that. It's okay, Nick. But it's okay. Just, yeah. Oh. Well, at least give it a shot on your own then. Like, at least try, which I'm sure maybe you are. I'm just saying in general. If you're not sure, then you should ask questions too. No, please ask questions. Like, that's where we're here. And if not, then if it's too many questions, then office hours, or I'm there. Or you can make office hours with me. Okay. All right, let's continue. So we're kind of going to go through this a little bit faster, which is not that important really, but basically there is a wavelength or wave behavior. So we know that the photons behave as waves and particles. The truth is, and this guy DePaolo proved it, that everything could have a wave-like nature. And it could be represented by DePaolo's wavelength, or DePaolo wavelength equation. So he said that everything kind of has a wave functionality to it because of like string theory and stuff, advanced stuff. But he came up with this. I don't like DePaolo wavelength, honestly, but it's true. So like they're sounding like, oh, this phone has a wavelength. Yeah, technically it does, but the object is so massive compared to a photon, it's completely negligible. And the wavelength of an electron, for example, is so small that it's negligible. So even an electron is so freaking tiny, and using this equation is too much for an electron. So basically, we consider it to have no wavelength. So that just goes to show you that he came up with something. And yes, Josh, after the Bohr wavelength. So he came up with something, but I mean, honestly, it's not too relevant in chemistry. It's not, but in physics it is. But anyway, here's the wavelength equation. He equated that the wavelength was inversely proportional to the momentum. So meaning if you have a lot of momentum, you're going to have a lower wavelength and a higher frequency. That makes sense, right? Because things that are fast usually have more energy. If they have more energy, they're going to have a higher frequency and a lower wavelength. So conceptually, it makes sense. And what you would do is basically just put everything into the formula. This is a simple plug and chug. So H is Planck's constant. That's the 6.626 times 10 to the negative 34 joule seconds. And then you have M and V. So you recognize those from physics, right? So M is the mass. In this case, this V is actually the wavelength. Is it? This is actually V. They made a mistake here. That's actually V. Yeah, they wrote the, I hate when they do that. This is actually velocity. Because we're talking about momentum here. That's velocity. It should just be V. This is new. Anyway. Okay, so another question. Yeah, you're right. I should have put P, because P is momentum. So proof that electron had waves came back years ago when they had a beam of electrons would produce an interference pattern. So if you take a beam of electrons and you put it through, so I said for electrons this wouldn't occur, and that's true if the slits are really far apart. But they put these two slits extremely close together, and they saw a little teeny bit of a interference pattern-like behavior, which suggests some kind of wave behavior for electrons. But it had to be very, very close slits. So it was very, very small wavelength. So almost none. But it was observed. Okay. So another thing, so I mean, these are just like little tidbits kind of thing, and we're going to stop we're going to take a break in like 5 minutes, but we're just get these little tidbits that aren't insanely important. So when you have this guy Heisenberg, right, he came along and he said that
It's like a pain in the butt.
when you try to observe an electron, you can't observe its position and its momentum at the same time. So you either know where it is or you know where it's going. You don't know both because of how fast and elusive electrons are in not really scientific terms, basically. So what he came up with was the uncertainty principle, which I don't think you're going to be using this equation, maybe on the homework 1 or 2 times, but basically he said there's both uncertainties in position and speed, and they're inversely proportional to the mass. So, and that makes sense because if you have a larger mass, it's going to be slower. So it's going to be inversely proportional. So he came up with that I'm not sure you get this equation, but the uncertainty in position, meaning the relative range of position, this is actually a cross product, not a multiplication with, because it's a vector, but whatever, times the momentum range, which is the mass is constant, but the velocity could range, you know, the speed of it. It has to be greater than or equal to Planck's constant divided by 4 pi. Why all of this? I'm not doing a proof. I don't even know the proof. Well, physicists know the proof, but not important for chemistry. So basically, the important thing is all conceptual here, is to say that you cannot know the exact position and speed of an electron at one particular time. The more you know about one, the less you know about the other. And that's all related to Planck's constant over 4 pi. So the uncertainty has to be less than that or greater than that at all times. There's always an uncertainty. So yeah, and this kind of ties into what we're going to talk about next, where electrons are actually not in energy levels like we think they are. So we talked about the energy levels being energy level 1, 2, 3, 4, but it's actually a probability distribution of electrons. So what that means is if you have hydrogen that has 1 electron at energy level 1, the chances are the electron is very close to the nucleus around energy level 1, very close in. But there's a chance that electron could move a little bit further out. The further you go out, the smaller the chance that it's going to be there. So that's what we call a probability distribution. If you take that probability over 1 billion hydrogen atoms, you get a bell curve or a distribution curve. And it could look like this. So here you have, I'll blow this up a bit for those of you at home. So perfect example because I love baseball. So who's that? It's Miguel Cabrera. Yeah, it's Miguel Cabrera. And probably gonna hit the ball. So we have here strike zone, well, strike zone's also over here, but where the catcher is setting up, right over here. And the chances are, let's say this pitcher is pretty good, chances are the ball's gonna be thrown in the strike zone. So the probability is higher in the middle. But there are cases where the ball is thrown really outside of the strike zone or outside of the target. There's a chance, but it's a smaller chance, maybe 20%, whereas the inside is 40%. And I guess this is the total, meaning everything, 70%. So that means if you do the math, there's 20% inside, 40%. I guess that's 60%. No. Yeah, 60% on the inside, 70% total here. Those percentages are stupid. But anyway, you get the point that most of the strikes are going to be thrown, right? So chances are for hydrogen, all of its electrons are going to be in the middle. But there's a small chance, that they lie outside of where they're intended to be. This is called probability distribution. So if you were to look at the distribution chart on the right, you would see that the number of particles closer to the strike zone is very high, or the percent chance that they are there is high. But as you move further away, it gets lower. That's exactly what happens with electrons. That's basically all I'm trying to say. So any questions on that? Just know that everything we learn about electron energy levels is not entirely true. But because it's always a model, right? So we're trying to make this digestible for students, for even grad students. But in reality, once you go beyond into the PhD level, you realize that really these equations are so flawed because they assume so many things. Like in physics, with your mechanics, the frictionless massless pulley, right? We assume so many things. Same applies here. Same applies with ideal gases. All right, so you have Schrodinger's wave equation. So this guy, another guy, Schrodinger, came along and he said that some of these electrons behave in a, this isn't a wave. So a wave function is different than a wave. So a wave function is a probability distribution function. So he plotted these functions of where the electrons could possibly be. And yes, Adi, his cat, Schrodinger's cat, he's dead and alive at the same time. That's where that comes from. Yeah. So, so with Schrodinger's cat, we'll talk about that. The idea is that there's a probability that if you have a cat in a box and you don't open the box and you're uncertain if the cat is dead or alive, the cat is both dead and alive at the same time. That's it. Until you open the box. But the idea is with Heisenberg's uncertainty principle, you can't open the box because then you would know where it is and like the speed of the whatever. Like if you take it to electrons, the speed of the cat and the position of the cat. But the idea is you can only know so much about the box. So you have to assume both cases or an average of the cases. So dead being one case, alive being another case, you assume the average of that. Same thing with the position and the velocity of electrons. And you assume their average of them is where they are, most likely. And that's what Schrodinger's equations mean, yes. Yeah, that's a really good question. And my knowledge is limited too. I guess into hardcore physics. But so how do you know? Here's the question. So how do you know that you can't know the position and the speed of an electron at the same time? No one's seen an electron before. People detect electrons. There's many instruments that detect electrons, even singular electrons like mass spec. But no one's actually seen one. You can detect where its position is based on different charges and different electron densities. But when you do that, since it's moving so fast, its velocity is different now. It's in a different spot. It's a completely different state, if that makes sense. So like, hard to explain. It's all quantum stuff. It's hard to explain. But if it's in a different, not really different spot with the same speed, it's in a different speed altogether. So let's look at do we have a probability distribution? Yeah, so in this probability distribution thing, right? Let's say you observe an electron in this position. As soon as you observe it in that position, it could be at any position with a different velocity. So you know it was there, but the velocity has one of these too. Has one of these distributions. So you can't know both because it changes so quickly. But you can know one at one time, if that makes it a little bit more clear. Okay, yeah, it's weird. I'll just leave it at that. All right, so we're gonna take a little break here because I know you guys are probably sick of this because it's all weird stuff. So just know the equations and everything that we stressed, right? So when we come back, we'll 7:20. We'll go to 7:30. We'll come back. We're going to learn about orbitals and quantum numbers are going to be the main thing. So how these electrons, their probability distribution could be even more specified into atomic orbitals and their quantum numbers, meaning the kind of quantum coordinates in those orbitals. So that'll make more sense because we're going to equate that to periodic table later on in chapter 9. Basically what we learned so far in this lecture. I know it's been tough because it's a lot of jumping around different quantum concepts and things like that, but let's break it down into bullet points. First bullet point, electromagnetic radiation has wavelength and frequency. They're inversely proportional. So wavelength is high wavelength, low frequency. High frequency, low wavelength. High frequency, that means danger. That means a lot of energy. So you can, so I should put that in there. So calculate energy of photon from frequency using the Planck constant times the frequency equals the energy of the photon. Also, you have the wavelength times the frequency equals the speed of light. Electromagnetic radiation, they're all in the form of photons. So there's just different wavelengths and frequencies of photons along the entire EM spectrum. Photoelectric effect. I think I explained that part pretty well, but you have the metal, which has a minimum energy that is needed to knock off an electron from that metal. It's called the binding energy. Photons that have more than that energy can knock off the electrons and give them kinetic energy. Therefore, the equation is the energy of the incident photon equals the binding energy plus the kinetic energy that it gives to the released electron after the incident photon hits the metal. So that's the photoelectric effect in a nutshell. Then you cannot know the position and velocity of a particle at a certain time. Just that's it. Next one, you can determine the amount of energy of an electron at a certain energy level of any element using the Bohr equation. So that's where you have the negative 2.18 times 10 to the negative 18 joules times n squared, or sorry, z squared over n squared. So z squared is your atomic number, n squared is your energy level. So in that case, you could also determine, so calculate energy lost from electron going back to ground state. Meaning, let's say, for example, i.e., if you go from energy level 3 to energy level n equals 2 to energy level 2. So that's that. And then you can use both of those equations, subtract the energies from each other, and you get an energy that is released. That energy is released. So released energy, you can calculate the frequency and wavelength of light released or emitted. And then you can deduce the color from that. Color. All right, then that's basically it. So then what we're going to learn now is we're going to expand upon the concept that electrons are positioned in orbitals. Orbitals have types, numbers, and what types of numbers? Those are quantum numbers for positions. All right. So hopefully that summarizes it pretty well. I'll leave this up there. I'll just, I'll leave that up there. All right. So the wave equation is our attempt to determine the best way to think about them is the quantum coordinates of the electron. Kind of the position, pseudo position, but also has to do with angular momentum and the spin of the electrons. There are 4 quantum numbers, and each electron in an atom has different quantum numbers. And basically, it's a 4-point system of coordinates. And we're going to go through each one specifically, and we will go through what their parameters are and what they mean. And feel free to ask questions anytime. So the first one is the principal quantum number n. It represents the energy level, right? So that we have, and we learned about those already. Energy level 1, 2, 3, 4, 5. Basically, how far away, well, on a probability scale, how far away is the electron from the nucleus? Energy level 1 equaling close, energy level 5 or 6 far away. The angular momentum quantum number L. This tells us what orbital the electron is in. And we'll talk about orbitals in a bit. And it can range from 0 to n-1. So let's write this down now. Let's write down these rules so we have them fresh in our head. So the rules for n is that n is greater than 0 and it's an integer. So n could equal 1 up to billions and trillions, but it has to count by ones. L has parameters. Whatever n is, L could only be between 0 and n minus 1. And there's reasons for that. And once we tie all this, what we're going to learn today, into the periodic table, which we'll do at the end of class, you'll all be like, oh, I get it now. And this is the main concept of the class, or of this 2 chapters. So L has those rules that it can be from 0 to n minus 1. Then you have a magnetic quantum number. This tells you within the orbital L, which subshell is it in. So orbitals have subshells. Depending on what type of orbital it is, there's S, P, D, and there's F. There's 4 types of orbitals. Each of those orbitals has a different number of subshells. This magnetic quantum number tells you which subshell it's in. And the rules for this magnetic quantum number are it ranges from negative L to positive L. Any questions on that? So it could be if L is 5, that's too big. If L is like 3, that means ML could be negative 3, negative 2, negative 1, 0, plus 1, plus 2, or plus 3. You have a lot of choices. Then the next one is the magnetic spin quantum number. This tells you which direction is the electron spinning. And it only has 2 possible values. Those values are plus 1/2 and minus 1/2. Professor, how do you know which one it is? You don't. You guess. If you have 2 electrons that are in the same subshell, one of them has to be plus, the other one has to be minus. Doesn't matter which one. But the idea is that if you have 2 electrons that are spinning in the same direction, let's say plus 1/2, they will repel each other a lot and they won't like each other. If you have them spinning the opposite directions, that's how you get electron pairs. So if you've seen covalent bonds, maybe you've seen Lewis dot structures, which we didn't talk about in this class yet. But when you see those, you'll notice that there's different pairs of electrons. These pairs of electrons are spinning in opposite directions from one another because that's what brings them close together. If they're spinning in the same direction, you get repulsion. All right, so these are the 4 quantum numbers, and let's learn more about them. First one is n. So n is relative to the size and energy of the orbital, meaning the larger the size of the atom, the larger the orbital itself, the larger n it's going to be in, most likely. So it's symbolized by n, and it could have integer values, 1, 2, 3, etc. So now L. So the angular momentum quantum number L. It can be from 0 to n minus 1, like I said. So for example, if n equals 2, the possible numbers are 0 and 1 for L. And L tells you which orbital the electrons are located in. So each L number corresponds to a certain letter. And these are the letters of the orbitals. So if you have L equals 0, it corresponds to S. L equals 1 corresponds to P. L equals 2 corresponds to D. L equals 3 corresponds to F. Make sense? SPDF, 1, 2, 3, 4. Ta-da. That's it. Okay. Next is the magnetic quantum number ML. Now this one tells you which subshell, or meaning, like, here's the way they describe it. It specifies the orientation of the orbital in 3-dimensional space. What that means in layman's terms is that some of these orbitals are shaped like dumbbells, meaning they have the nucleus is in the middle. They have one part that has multiple electrons this way, another part that's going this way, another part that's going this way on different axes. It could be x-axis, y-axis, z-axis, or the x-z axis, different in-betweens. The idea is that this number tells you which one of those little dumbbells it's in. So do we have pictures of those dumbbells? Yes, we do. And we're going to learn about SPDF towards the end, but here we go. Here's what a p orbital looks like. So p orbitals, there's actually 3 of them. There's an x, there's a y, or there's an x, there's a y, there's a z. So these orbitals, how many quantum numbers are there going to be? Or how, sorry, no, that's not a good question. How many, yeah, so since there's only 3 orbitals, how many L values can there be? Or how many ML values can there be? Just 3. Meaning, if I'm an electron, I could be in px, or the y, or the z. So there's only 3 options for me. If I'm a d orbital is crazy. If I'm a d orbital, I actually have 5 choices. I could be in the x, the y, the z, the xz, and the xy. So, or if you can make it d squared, z squared, whatever. But yeah. So how you said 6 for, I think you said for p orbital. That's true. There's 6 positions, but here's the kicker. P orbitals. There's only 3 p orbitals, but each orbital has a place for 2 electrons. Or sorry, each subshell. My bad. I used the wrong terms. There are 3, or there's in one p orbital, there's 3 subshells. There's the px, the py, and the pz. Those are subshells. Each subshell holds 2 electrons. 2 times 3, 6. So that means P can hold a maximum of 6 electrons. And we will deduce this information and we will tie this to the periodic table and it will be awesome. So let's go back. All right. So these magnetic quantum numbers can be from negative L to positive L. So if you say L equals 2, the possible values for ML are negative 2, negative 1, 0, 1, and 2. These correspond to subshells in 3-dimensional space. So L equals 2, do you remember which letter that is? 0 is S, 1 is P, 2 is D. Good. So D. Good job, online. Nice. Good job, Nick. So if it's the d orbital, that means that if I can have these 5 possible ML values. That means in the d orbital, there is 5 possible subshells that I can be in. It can be in subshell negative 2, subshell negative 1, 0, 1, or 2. That's exactly what this means. So it's a set rules that narrows down the coordinates of the electrons in certain energy levels, orbitals, subshells, and then positions by spin, which leads us into our next one, which is not covered. Oh, there it is, which has its own slide. Good. Sometimes they don't. So magnetic spin. Now spin, once you're in this deep, you know exactly the energy level. You know the L, which tells you the orbital. You know the ML, which tells you the subshell in the orbital. The only thing remaining is whether it spins to the left or spins to the right, or spins up or spins down. And this is by M equals, or MS equals plus 1/2 or negative 1/2. And again, it doesn't matter which one's which one goes up or down, as long as one goes up and the other one goes down. So, and they both have to be in the same, they could both be in the same subshell that way. Okay. So here's what we're going to do to a little bit more detail. So, all right. So I'm going to tell you an energy level. N equals 2. What are my possible L values? Perfect. 1 and 0. Awesome. Good. 0 and 1, 0 and 1. Awesome. So 0 and 1, because it's the range. It could be anything in the range from 0 to n minus 1. So it could be 0 or 1. This is going to be L. This is going to be, we're writing a tree diagram, ML and MS. So now for L equals 0, what are the possible ML values? Audie's onto it. So yeah, it's 0. Since the rule for ML is Not quite. So, Nick, you're right for the next one. You're right for the next one. So hold that thought. Good. So for L equals 0, the range for ML is from -0 to +0, which just means 0. So ML is only going to be 0. For L equals 1, we have from -1 to 1. So this means -1, 0, +1. Like that. Then for MS, it's not a really good S. There we go. For MS. So now we know. Here's what we just did. Energy level 2 has L could either be 1 or 2. So L equals 0 or 1. So L equals 0 is what? S. It has an S orbital. And look, L equals 1. That means it has a P orbital. So we just figured out that energy level 2 has an S orbital and a P orbital. Great. The electrons could be there. Oh, so Ben, good question. So it could be any of the ones in the middle. It includes the ones in between. Yes. Yeah, it's not an endpoint, it's a range. So for L equals 0, the only option is ML equals 0. This means that the S orbital has only one subshell. That's exactly true. So S orbital has one subshell. That one subshell, what are the possible MS values for that subshell? It could spin up, it could spin down, right? So +1/2, -1/2. +1/2, -1/2. So it's saying that there are two possible values in that subshell, meaning there are two possible electrons in that subshell. So each subshell holds 2 electrons. Now for P, we have L equals -1. For L equals -1, there's also a +1/2 and a -1/2. Same for 0 and same for +1. So for any subshell, whether it's S, whether it's P, whether it's D, whether it's F, you have a possibility of 2 electrons per subshell. Now, you can add up all these possible electrons and you get 2 electrons, and you have the P orbital, which has 3 subshells, times 2 electrons each equals 6 electrons. And then you also know that for every possible electron in n equals 2, you have a total of 8 electrons that are possible. That are the maximum. 8 electrons max. So the maximum electrons that can have an n equals 2 energy level is 8. Because of this, because we can break it down by quantum number. The L number tells us if it's S or P or D or F. The ML tells you how many subshells there are, the possibilities of their subshells. And then the MS tells you spin up or spin down, basically 2 electrons per subshell. All right, questions? 1 second, the online things. Yeah, okay, yes. Like in the atom? Okay, perfect. Good question. So her question was, what does it look like in the atom? So here we go. 3-dimensional plot, you have X, you have Y, you have Z. Or actually, it should be the other way around, but whatever. So nucleus is in the middle. Let's talk about a p orbital. That's easier to know. So p orbital, we have 3 subshells. They look like this. Subshell 1, subshell 2, subshell 3. In each subshell, there's 2 possible electrons. So, and they have to be spinning in opposite directions for them to be in the same subshell. So electron 1, electron 2, electron 3, electron 4, electron 5, electron 6. That's what we mean. Now, an s orbital, there's only one subshell, and that subshell is actually shaped like a little sphere. That's why I didn't do this example, but it's a little sphere around the nucleus. And there you have two electrons. One would be on one side, one would be on the other side. For D, it's just more dumbbells, and for F, it's a lot more dumbbells. So it's just more complicated. But that is how they look like. And based on the energy level, N, that determines the distance of these, or basically the length of these subshells. So let's say this is N equals 2. You can also have an S and a P orbital for N equals 5. You totally have that. Once you look at the periodic table, you'll see. But before that, this is what it would look like. A P orbital for N equals 5 would just be meaning the electrons are further out. Same thing, they're just further out. So what we can deduce from a large atom is that it's a summation of all these different orbitals, all these balloon animals, basically, in different energy levels. Some are at 3, some are at 4, some are at 5, in different positions. That's what this means. A very good question, too. Okay. So, any other questions? I know this is a lot. All right. So, here's a good chart that sums it up. Now, if you had, let's go to a bigger energy level 3. Energy level 3, you have a new L value. L could be 0, which we've seen as S. L could be 1, which is P. L could now equal 2, which is considered a D orbital. Just following the rules, we can figure out the amount of subshells and the amount of electrons. So the amount of subshells, meaning ML, is 1, 2, 3, 4, 5. Because if we know that L equals 2, ML has to be -2, -1, 0, 1, or 2. So if that's the case, how many electrons are allowed in a D orbital? Good, perfect, 10. Because there's 5 subshells, 2 electrons per subshell. So 10. Good, so times 2 equals 10. So next, when you go to N equals 4, you have L equals 0, which is S, L equals 1, which is P, L equals 2, which is D, L equals 3 now. 3 represents F. So in F, that's L equals 3, you can have the possible ML values as -3, -2, -1, 0, 1, 2, 3. So how many so this should be subshells. Just not to throw off the terminology. You have 7 subshells. How many electrons that are possible? Max. Good, 14. Because there's 2 electrons per subshell. Ta-da, perfect. Okay, does that make sense? All right, so basically we're just trying to see where the electrons go in the element or in the atom. Once we get to the periodic table, this will make a lot more sense. Trust me. All right, so we have that. Okay, so here we go. Here's a good question. How many electrons can be described by the quantum numbers N equals 3, L equals 3, and ML equals 1? I'll give you a minute. First one to answer doesn't really get anything, but I'll give you a good job. Remember the rules. Oh, we have an answer. We have 2 answers. 0. Good job, Nick, and good job, Adi. Awesome. Good. The answer is 0. Tricked you. Yep. Boom. Because ML. Wait, no, not ML. Because L. Oh, yeah. Because L. Yeah, because L has to be between 0 and N-1. Good, Nick. It can't be 3. And good, Lewis. So it can only be 0, 1, or 2. It can't be 3. So that's why this whole set is null and void. Guarantee you on the test. Tell you right now. They're going to give you a question. Which of the following combinations of quantum numbers is not possible? So you have to go through the rules and see, is this one possible? Is this one possible? Is this one possible? Based on the rules. So the answer for this one is 0. Good. Oh, look, we have that question. All right, so I'll give you another minute. Or just whoever gets the answer right first gets nothing. It gets a good job. Oh, we have answers, A and A. And yes, that is right, because of the same reason, because L cannot equal the same thing as N. Good. We're getting good at this. Good. All right, so A, awesome. Aha. So now I'm going to leave this to you for a couple minutes. How many electrons are possible for n equals 3? And in your notebooks, draw a tree diagram like we did for n equals 2. You might need a little more space. For n equals 3, we're doing. So draw like a tree diagram to see how many electrons are there. So remember, you're going to write the possibilities for L, the possibilities for ML, and the possibilities for MS for each ML. Good job, Nick, and good job, Adi. So we have 18 is the answer. So I'll write it down, and you can finish off your chart as I'm writing it down. So n equals 3, not M, M. N equals 3. So we'll write L, we'll write different tiers. ML, we'll write MS. So L could either be 0, 1, or 2. ML for 0 could only be 0. ML for 1 could be -1, 0, +1. ML for 2 could either be -2, -1, 0, +1, +2. Now the MS's, you have 2 MS's for each ML because it's a spin up and a spin down. So I'm not going to write every one of them. I'm just going to do this. Or you can just multiply the number of MLs by 2. So you have 1 ML, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 2 equals 18 electrons, max. Any questions on that? No? Okay. Let's continue. Orbitals and their shapes. Oh, there's a chat. Yes, Josh. You with the math, man. You with the formulas and stuff. You like formulas. But yeah, so the equation, if you want to know, it's 2 times n squared. That's how many electrons are in each orbital. Or each energy level, sorry. You thank Josh for that. The equation. You must be an engineer. All right, so probability distribution, we talked about that. So basically how that works is, this is an s orbital. So the probability distribution for an s orbital looks like this, meaning it's probably going to be in there, the electron, but we don't know for sure. It could be close, it could be really far away. Oh, game programming, yeah, that's why. Yeah, because you're the programmer. Engineer or programmer. That's two. Programmer is actually more fitting for your equations. You want to code everything, all these equations. Well, chemistry can't be coded. Well, it can. And there's resources for so I do a lot of computational modeling for different molecules and proteins and stuff. So you can calculate it, but it's not as reliable as doing the cell work. It's a lot of new revolutionary stuff that's coming out on software. Anyway, so here's the s orbital, L equals 0, right? You have probability distribution. We all know what that is. Then we have the p orbital. So the p orbital has 3 shells. They call them 3 orbitals. So like the p orbital has 3 orbitals. I'd rather not say that. I'd rather just say subshells. So it has subshells in the orbital. And then each of those, px, py, and pz, has 2 places for an electron, meaning a total of 6 electrons for the p. That's an important thing to know. So on the side here, you should write the s can have a max of 2. So I'll write max E minus, 2, P is a max of 6, D is a max of 10, and then F is a max of 14. Those are important to know when we relate this to the periodic table. And you'll see exactly why this is the case. Well, the thing is, like, this was just so interesting about this. We saw why that's the case when it came to the rules of quantum numbers. Now we're going to see why that's the case when it comes to the organization of the periodic table. And they both coincide with each other, which is crazy. So we learned about how the periodic table is kind of organized pretty well, right? The best we can do. But this opens up a new window of how well it's actually organized. It's crazy. These are p orbitals. D orbitals are just more complicated. There's 5 of them. So they call them dxy, dyz, dxz, dx squared minus y squared, and then there's dz squared. So there's 5 of them, 2 electrons per dumbbell, 10 electrons. So here they are. Then you have the f orbital, which is even more complicated than the d, and you have ml equals 3, or sorry, L equals 3, ml equals -3, -2, -1, 0, 1, 2, 3, 7 possible values with, so that means 7 times 2 equals 14, so 14 possible electrons, and it's a bunch of craziness. Some of the subshells do this, they go around and they do this. This is called the fz cubed minus 3 over 5 zr squared orbital. Get out of here with that. That's not important. But basically you have a lot of balloons, balloon animals. I'm gonna take that part out of the YouTube video. I don't want my boss hearing me say they're balloon animals. So this is, back to your question, Yasmin. This is why atoms are spherical, because they have this, like this organized arrangement of electrons, and they all go in opposite directions based on the repulsion of electrons. Everything evens out so that it ends up being almost completely spherical, almost perfectly spherical. And now the big question is, how do all these quantum numbers relate to the periodic table? So now get ready to get your mind blown. In the next chapter. I purposely left that as a cliffhanger, but I want to fill in the cliffhanger for your understanding purposes. Periodic table. And it's got the S, got the P, got the D, got the F. That's all annotated. So what we can do is we can figure out, from knowing all of this information about quantum numbers, we can figure out the quantum numbers for all of the valence electrons in every atom. We can figure out the electron configuration of every atom, meaning where the electrons are, SPD, energy level 1, 2, 3, 4, whatever, of every single atom or every single element. Now let's take a look at a periodic table that has things on it. This we're going to be doing most of next week, but here we go. So let's take sulfur. Perfect. It's right there for us. So let's try to figure out the electron configuration of sulfur. Here's how you do it. Now, sulfur has the atomic number of 16. This means that in neutral sulfur, we're going to have 16 electrons. The atomic mass is 32.06, doesn't matter. But all we care about is the protons and the electrons. More importantly, the electrons. So we know that our electrons have to equal 16. How they're broken down is you basically, I love saying it like this, you just read the periodic table like a book. From the top left, scan it across, next line, scan it, next line, scan it. And we're going to write this annotation. So we go to 1s. This position of hydrogen is 1s1, meaning it is energy level 1. It is the s orbital, which means L equals 0. And it is the first position. So you could say ml equals 0 and ms equals -0.5, whatever. So we can say this is 1s1. We could then say that where helium is 1s2, meaning it's in the same orbital, the electron's in the same orbital as the hydrogen electron, but it's in the second position, the opposite spin position. So we can say this is the entire s orbital. We went right through it. We're going to go through every orbital required to get to sulfur. So this is called 1s2. Next, so we did this. Next is 2s. Same thing. We're going to go right through it. 2s1, 2s2. So we write 2s2. Scan, 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 scan. Oh, look what we got, a p orbital. Where's sulfur? It's on the second one, or what we call 3p. P doesn't start at 1. P starts at 2. P starts at 2 because that is the first position, or n equals 2 is the first position that L could equal 1. It all ties in. So I'll say that again. P starts at 2 because when n equals 2, so just to reiterate, when you have these numbers in front of the P, or in front of the numbers in front of the letters, meaning 2p, that 2 represents the n, the energy level. And it's very synced up with the period for the most part. Not for D and F, but for the other ones it is. So the first p orbital that occurs is n equals 2 because the L value of n equals 2 is the first. That's the first energy level that L could equal 1. And remember, L equals 1 is a p orbital. That's the first time that could happen. For n equals 4, 5, for n equals 3, 4, 5, 6, etc., p could always be 1. But n equals 2 is the first time that could happen, not n equals 1. So what we're going to write here, we're going to go through this completely. Go through all of these 6 elements. And oh, there's 6 elements, right? How many electrons are possible in a p orbital? 6. Mind blown again, right? Because each one of these elements represents an electron in a p orbital. So we can write this as going through this. We can write it as 2p6. Now go through again. 3s, same thing. Each s orbital we know holds 2 electrons. 3s2. Next, we go across, and oh look, we're at the row of sulfur. So what would we put here? This is called 3p, but what would it be? Good, 3p4. 3p4, because we go 1, 2, 3, 4. 3p4. Ta-da. This is the electron configuration for sulfur. Boom. And it's all based on the quantum numbers and the position. Now, the electron configuration itself is pretty easy, right? All you have to do is just read the periodic table like a book and write it in this funky notation. That's exactly it. There are a lot of different nuances and little tricks and some exceptions that we'll learn more about next class. But before we leave, we'll do one more. We'll do cadmium. This one's a little bit more difficult. Now cadmium, we'll do the same thing. We'll go a little bit faster. 1s2, 2s2, 2p6, 3s2, 3p6, because now we're here. 4s2. Now, what happens now? It's not 4d, it's 3d. 3d, how many electrons are in D? 10, good. So you can count as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then we have, we'll write on the next line, 3d10. Then what comes next? 4p6. Then what comes next? 5s2. Then what comes next? 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, cadmium, 10, 4d10. Boom. That is the electron configuration for cadmium. Now, for the d orbital, it's weird because you notice how s and p, they kind of go, they follow the same thing. The same line is, it goes 2s, 2p, 3s, 3p, right? But for D, it goes 4s, 3d, 4p. It goes 4 to 3 to 4 again. That's weird. But the reason why that is because quantum numbers. N equals 3 is the first position that the d orbital occurs. That means L could equal 2. That's the first place it could happen when n equals 3. a good question would be, oh, professor, why didn't they just slide the d orbital up one more? And the answer to that would be because that would ruin every other trend of the periodic table. So again, this is a model. And if we were to move the d orbital up here, then you would have, then the atoms wouldn't be in order, because these atoms they wouldn't be in order in terms of protons. That's the main thing that determines their position on the table, is the proton number. So yeah, so just remember that. Yep, 4D is on period 5. How inconvenient. Exactly. Yeah. So they're lagging one behind. So the S and the P's are synced up with the period. Here's the way I think about it. The S's and P's are synced up with the period 1 through 7. But I mean, we know P doesn't have 1, but it has 2 through 7. D is one behind. So wherever the period is 4 or 5 or 6 or 7, D is 3, 4, 5, and 6. So it's one behind. And then F is 2 behind. So the F orbital goes here. So when you have 6s, you're actually going to go 4f. So it's 2 behind. But F orbitals in general are really weird, and I'll explain it a lot more. I'll explain a lot more clear next class. But in general, this is how you do configuration. Other things, the reason why at the beginning I wrote the number of electrons of sulfur is because you can check your work. You can count up the number of exponents, and that's the number of electrons. So you have 2 plus 2 plus 6, that's 10, plus another 2 and 4, that's 16. So you get 16. So that's another way to check your work. On the homeworks, you may see them written differently. So for example, there's 2 more things I want to say. This one works out fine, but in this case where you end up with d orbitals, sometimes they like to write the 5s2 last because it's the highest number. It makes sense. That's just a different way. As long as you have the same stuff in there, it doesn't matter. Also, some of you are probably thinking, what the hell, if I have to do something like hafnium, I'm going to cry because you have to write all that stuff. The answer is there's a shortcut. Yay. Shortcut, it's pretty easy. So we're going to do that shortcut for cadmium. If you go back and read backwards of cadmium, you have 4d10. So we read backwards, boom, 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 we're here. 5s2, we're here. And then where do we end up? If we go back one more, we end up here. This is Sparta. No, this is xenon. I don't know. You have helium, you have neon, you have argon. Yeah, it's probably xenon. Yeah, so you have xenon. So what that means is you can write what we call the noble gas configuration. So that means you can take all this stuff that happens before xenon and bundle it up as xenon. So we can say that the actual configuration for cadmium is in a bracket XE. So you can basically bundle up all this stuff that we wrote as bracket XE. And you can only do that for noble gases. And then whatever's remaining, 5s2, 4d10. And that would be the what we call the abbreviated configuration. So instead of writing all that stuff, especially when you get to the f orbitals, it gets a lot. So you can write abbreviated. That is completely acceptable too. They're identical. Any questions on that? No? All right, one more thing, and then we're done. Because I know it's a lot. From this configuration, we can tell the number of valence electrons. So the number of valence electrons, well, who remembers? So what's a valence electron? We talked about it, right? With bonding and everything. So what's a valence electron? Good, outer shell, right. So I used to throw out that term when we talked about them, but you didn't know what outer shell meant until right now. Outer shell means the highest energy level. So out of all, I know it's kind of sloppy, but out of all of these electrons in cadmium, How many valence electrons does it have? Trick them. The highest energy level. So for you guys, so you're looking at 4d10, right? Is 4 the highest energy level? That isn't. Yep. 5. Even though 5s2 comes before 4d10 when we're writing it out, it's the highest number energy level that has the valence electrons. So that means it would be further away from the nucleus. So yeah, that's important to know. So we're going to learn so much about this next class. So yeah, how I got you how. So yeah, it's actually 2 because so 5 is the highest energy level, the N, highest N in cadmium. There's a lot that we can do with these electron configurations. We can add electrons to it to make ions. We can subtract electrons from it to make ions. We can, there's rules that sometimes you have to move electrons from one orbital to the other to make it more stable. It gets kind of complicated, but we're going to learn about it more next class. So for sulfur, it's 6. Yes, for sulfur, it's 6. Good. So sulfur, for valence electrons, we have 3s2, 3p4. 2 plus 4 is 6. And guess what? That coincides with the rules we learned about valence electrons. 6a. How many does it have? 6. Boom. Everything comes together.